Okay. Any questions so far? This is mostly standard material. Let's keep going. What is this? Joint entropy of independent random variables, right? So, if you have two random variables x1 and x2, which are independent of each other, then you can define their joint entropy. So one thing that's useful to think about, which in math, even programming everywhere, right? Like you have two things, but you have x1 and x2 are individual random variables, but their pair, the tuple itself, is another random variable. So the entropy of the tuple is just the entropy of the tuple. Like you don't even need to worry about like the individual random variables, right? You just think of this pair as y, right? I can just call this whole thing as y, and then this is y. So just in terms of thinking about, like, if you see a more complicated object, just think of that whole big object as your y. Okay, those who are able to follow. How did I get the second step from the first step?
Because like the two random variables are independent, so then the joint probability is just static.
Yeah. So correct answer is that since x1 and x2 are independent, the joint probability factors out as the product of the individual probabilities. Great. So we know this. And then we know the log properties. If you have forward-end properties of log, please revise them, and that they will be helpful. Right. So at the end of the day, you get that the entropy of the two variables is same as the sum of the entropies. So what we are saying is you have two random variables that are independent. So the total information contained in them is the sum of their individual informations because they are independent. If they were not independent, then something else will happen, and we'll talk about that in a future lecture. Okay, so we already saw the first statement that if x1 and x2 are independent, then the joint entropy is the sum of the entropies. How many of you have heard the term IID? Okay, that's good. Yeah, so IID is a very common term which means independent and identically distributed, right? So you have n variables. They are all mutually independent. So not only pairwise, but like jointly, they're all mutually independent of each other. And each of them have the same distribution. So we'll often use this notation. So what this is saying is xn is an n tuple of x1 ... xn. Each of them have the same distribution as x. X is sort of a placeholder random variable, which is just denotes the distribution of all of these guys. So you are like maybe tossing a coin n times, right? So each of the coin toss is an independent random variable with the same distribution, with some Bernoulli half or Bernoulli p. So then using the same thing sort of inductively, you will get that the entropy of the n tuple is n times the entropy of a single random variable. So entropy just adds up if you have independent random variables. If you don't have independent, then we'll talk about it in lecture 8. It's a very important use case, but for now, let's keep it simple. Any questions so far? Okay. Another quantity, don't be scared. This is called KL divergence. So this is defined on two random variable, two probability distributions. You have P and you have Q. Both are on the same alphabet. So both are on 1 to K. So P is like P1, P2, P3, Pk, and then Q is like Q1, Q2, Qk on the same distribution. So then this divergence or distance or relative entropy between P and Q is defined as this thing. I will not talk about it for now. Just you will have some examples in quiz, solve some questions, right? It's just something Pi log Pi by Qi, the sum of these things, right? Doesn't tell you much, but the properties will tell us much more. Okay. There is only one property we need, that it is positive. It's greater than equal to 0 with equality if and only if P is equal to Q. So it is in a way a distance between two probability distributions, right? If the probability distributions are similar, it's smaller. If they are not similar, it's bigger. Right? So it's a way to describe the difference between two probability distributions. Proof is in lecture notes, uses convexity, Jensen's inequality again. Yeah. So just remember this. We will just need this property one time in our proof later. So that's why I described it. So KL divergence, Kullback-Leibler, the two people who came up with it, or relative entropy is a measure of distance between two probability distributions. It is not symmetric. So like when you think of like your functions, typically like distance functions, like Euclidean distance or L1, L2, L0 or something, most of them are symmetric. So between X and Y and X, it doesn't matter. Here it does matter. You'll see it in your quiz. So this is in general. It's not equal to DQP. It's fine. It's just a fact. How many of you have seen it actually? Some of you might have seen it in your machine learning classes. If you have done generative models especially, this comes up a lot. And why does it come up a lot? Because this is a distance between probability distributions, right? So all of these generative models, what are they trying to do? They're trying to, your LLMs and diffusion models and so on, they're trying to generate samples which are similar to the real distribution, right? They're trying to create human-like text. They're trying to create artistic-like images. So, but to compute the loss, like how far they are from the real thing, you need to have a loss function which determines how different two probability distributions are. And for various reasons, including the fact that it's like differentiable and everything, KL divergence is like the loss function of choice in many, many cases. So just mentioning it, you don't need it for now, but yeah. And it has some interpretation in compression, which we might talk about, or it's in the notes definitely. Okay, we'll move on from this. For now, just remember this one thing, that the KL divergence is greater than or equal to 0 with equality if and only if the two distributions are equal, right? Rest of it is just general knowledge. Okay, so we are here. So the main result of lossless compression, right? So information theory is like one of the fields where you will see results which are like very, very precise. You know exactly what's happening. For every prefix code in the world, the expected length is greater than or equal to the entropy. There is no prefix code for any distribution, right? There is no prefix code that can beat entropy. You cannot go better than entropy. Entropy is the fundamental lower bound. So this result is called a lower bound, or it's called a converse. And not only this, right? If I just gave this and then I didn't give you like what can you do, that would like this is a negative result in a way, right? This just tells you can't do better than entropy. But there is another result. You can achieve entropy. You can get arbitrarily close to entropy. And we will talk about maybe today or next lecture about what do you mean by arbitrarily close with prefix codes. So this is the achievability part. I will stop here for a minute. I'll let you digest this and then we'll on. Okay. Any questions? Good. Right. So what does this mean? Right. This means that entropy is the fundamental limit of lossless compression. It's a very powerful result. And like the next several lectures, what we will be doing is trying to actually achieve entropy. All of the work, like basically lossless compression. So Shannon in his 1948 paper, he showed this result. He showed that you can't do better than entropy. And like next 50 years, even like as soon as like 2014 or something, people are still trying to find more and more efficient ways to achieve entropy. All of your lossless and lossy compressors at their very root have something called an entropy coder. Entropy coder is something that is just trying to achieve the entropy of whatever the input is. And you have Huffman codes and you have arithmetic codes, you have ANS, you have this and like a bunch of different ideas, all of these trying to just do this, try to achieve entropy in an efficient way. Actually, like, so after Shannon, like proved this result, I think it was almost 30 years before somebody was able to come up with a method that was a linear time in computational complexity way of achieving entropy. And then more recently, people have like improved that. It's still linear time, but like better for modern hardware. Okay. Same result applies to the more general class of uniquely decodable codes. So if you noticed in the last lecture, I said for every prefix code, you cannot beat entropy. But actually for any lossless code, any uniquely decodable code, you can't beat entropy. Entropy is the fundamental bound of lossless compression, whether or not you want to use prefix codes. This you will prove in, this part you will prove in the homework. And the last point is that we are, as I mentioned like a little bit before, we assume here that your things are independent, identically distributed. Don't think that like this is only useful in very specific settings. No, this is useful everywhere, and we will see it again and again. However, more specifically, we will study more general distributions in lecture 8 to 10. So a bit later. For now, we'll just stick to the IID case. Okay. Any questions so far? We'll now go to the proof of this result. I think the proof is not as exciting. I think really what, if you understand this result, right, the enormity of this, I think that's the main point. The proof, we will do the proof. Some of you will like it, some of you will not. Okay. Let's do the proof. Actually, proof will give you something very useful. So yeah, let's do it. Well, okay. So first we'll prove the converse. Converse is that you cannot do better than the entropy. Any prefix code in the world cannot have expected code length that is lower than the entropy. So we start with our usual regime. We assume that X is distributed according to some distribution P, and you have a prefix code with certain lengths. And what we'll try to show is that, so what are we trying to show? Let's write it down so that it's very explicit. We are trying to show that summation I equal to 1 to k pi li is greater than equal to the entropy of P. Okay, so now some of the proof will be very like, why are we doing this? But we will do it anyway. So now let's define Qi as another distribution where Qi is defined as C times 2 power minus Li, where C is defined as this quantity. So here you see I wrote that C is equal to 1 over summation 2 power minus Li is greater than equal to 1. Can somebody explain why this holds? Yes. So the answer is that this is Kraft's inequality, right? So we said that we will prove this for prefix codes, but somewhere we need to use the fact that it's a prefix code, right? Like it's clearly not true for general. Like if you didn't want a lossless code, you could just have a code where every length is 0 or every length is 1. So yeah, like lossless codes can't be better than entropy. Your like non-lossless codes can be better than entropy, right? So this is where we will use the fact that it is a prefix code. A prefix code, we saw that it's like an if and only if condition, right? Prefix codes, if and only if Kraft's inequality. So we use this here. Good. Okay. And then we do a quick check, right? The C is like a normalization factor, right? Like oftentimes like you have something and then you want to convert it into a probability distribution. So you divide it by the sum so that it becomes a probability distribution. So that's what we did here. So summation of Q is just like this thing where you can, after you substitute the value of C, you will very easily check that the sum is actually 1 because the terms will cancel out. Okay. So with all this, what we did was we already had a probability distribution P, and now we created a new probability distribution Q, where Q has all these lengths inside it. So now we have two distributions, and we just read about a way of using two distributions. We will use the KL divergence, right? And we already saw the property that KL divergence is greater than equal to 0. So let's just use it. And again, right, like I didn't prove this quantity, but I'm not cheating. You can like read it. It's like a 4-line proof. You just need to know Jensen's inequality from convexity. So yeah, I hope you can trust me with this. Okay. So now math, just moving around terms. Yeah, I won't do it. I think it, just read it at home, like to understand like some of the moving of variables from here to there. Let me focus on the main parts. So here you write it down, write down the KL divergence. It's greater than equal to 0. Good. Then next step, let's write it here. So you basically split the log. Very simple operation, right? You move out the QI term here in the second term. Okay. Now this term, this left term is actually the negative of the entropy. If you remember the definition of entropy, it was pi log 1 by pi. So here you have not the denominator, so it's the negative of the entropy. Sorry. Okay. So from here to here, you move hx to right hand side, right? And I would encourage you to like go over it in peace at home. Then we had this term with a qi, right? We substitute qi here, so you get this c times 2 to the minus li. Then you have expectation. You can basically open up this log again, split the log, and let's not do this. Let's just focus on the result. Like after you do all of this, what you will get is you will get that expectation of the length is equal to this, which is greater than this term because of Kraft's inequality, which is greater than equal to entropy. So long story short, like this is what you get. This is the main result, that expected length is greater than equal to entropy, right? Don't worry about the like specific stuff. Like really, this is what we care about it. We get the result. It's just mathematical manipulations plus Kraft's inequality plus KL divergence positive. Like these are the 3 things we used. Now, oftentimes, like when you prove an inequality, you want to see when does equality hold. So let's do that. If you follow all the calculations carefully, you will see that there are 2 conditions you need. One is that C must be equal to 1. So now, let's go back to what C was. So this was C. So what does C being equal to 1 mean? It means that Kraft's inequality must be satisfied with equality, right? We saw before that, like we saw 2 codes before. One was a suboptimal code, and we saw Kraft's inequality was not satisfied with equality. And then we saw an optimal code where Kraft's inequality was satisfied with equality. So basically for an optimal code that achieves entropy, C has to be 1. So you have to satisfy Kraft's inequality. So let's write it down. So Kraft's with equality. Okay. And the second thing you get out of the thing is that pi must be equal to qi, which basically gives you the thumb rule. So you can achieve entropy if you can satisfy Kraft's inequality and you follow the thumb rule. You follow that length is log 1 over pi. So that's the fact basically. Yeah. So you cannot do better than entropy, and you can do equal to entropy if you satisfy Kraft's inequality and your lengths are log 1 over p. So you satisfy that thumb rule we saw before. Okay, let me stop here. And read it at home. It's easy. Don't read it. It's fine. Yeah. Just remember the results.
I'm just curious. I like those 2 things, like Kraft's inequality being satisfied in the equality, and then the probability to be.
Yeah.
Like, are those 2 things like almost the the same? Because like I imagine if the probabilities aren't exactly log 2, then class inequality wouldn't be satisfied. Like, could you satisfy class equality and still not have them be like perfect log 2 probabilities? Like, are those two the same or are they different?
That's a very good question. So one thing to notice is that Kraft's inequality is purely a property about the lengths. There is no probability in there, right? Kraft's inequality is just a property about the lengths of the prefix code, right? So it is independent of any distribution, right? So if you have a code that doesn't satisfy Kraft's inequality with equality, it cannot be the optimal code for any distribution. It's just a bad code, period. Like it's that's sort of one thing to think about. However, the thing you said is that for a given distribution, if you do not have Li equal to log 1 over pi, if you have Li's which are bigger than that, then yes, you will not satisfy Kraft's inequality. So, no, I take it back. No, you can still satisfy Kraft's inequality because, okay, maybe it's worthwhile doing a quick example here. Okay, so the question was like the two conditions for equality, are they the same, one and the same, or are they different, right? So basically, so Kraft's has no P basically, right? It's just a property about L, right? So now if I make a code which is like this, yeah, okay. So we already checked before, right, that this satisfies Kraft's with equality, right? So this here like summation 2 power minus Li, you can easily verify that this is 1. Okay, now if you take ABCD and you take the probability distribution, which is like this is 1 by 8, this is 1 by 8, this is 1 by 4, this is 1 by 2. You see, you can probably see that this is not the right code because D has the smallest probability, highest probability, but you are giving it a very long code word, right? So here you see that Li is not, Li is not equal to log 1 over pi, but it does satisfy the Kraft's inequality. So you do need both properties.
Yeah, that makes a lot of sense.
Yeah. Basically, Kraft's is just about the lengths and whether it's an optimal code in that sense, right? However, I think there is the opposite side, which I should mention that. And then we'll move on. Is that if Li is indeed equal to log 1 over pi, then you can do it very easily, some calculation, which is like you do 2 power minus Li, right? And then you put it in log 1 over pi, and you do the 2 power log thing, you get pi, and this is equal to 1. So this implies that Kraft's with equality, right? So one of them implies the other, not the, it's sort of situation.
I think that's kind of what I was like thinking about, like one would mean the other one, but it doesn't go the back.
Yeah. Okay, any other questions? Right. Okay. Now the other part. We said that not only is entropy like you can't do better than entropy, but you can do as good as entropy. So this is the topic of discussion for next several lectures. Today we will see like the start of the discussion. We already saw Shannon codes, right, which achieve this length, right? And we saw that if you achieve these lengths, log 1 by px, you are going to be very close to entropy. Just in the last few slides we saw. So now let's like make it very formal. So if you have lengths equal to log 1 over px C-link, then the expected length is this summation pi times li, which is summation pi times ceiling function of log 1 over px. Okay. Say this is, it's 1 over pi. Yeah. Now this is just like a general thing about ceiling functions, which you may or may not have seen, which is that ceiling function of x is bigger than or equal to x, and it's less than x plus 1. So it's like somewhere between these two things. So you can put the second part, we just need the second part, that the ceiling is less than x plus 1. So you get that the expected length is less than pi times log 1 over pi plus 1. So you get this plus a second term. What is the second term? What is this term? Summation 1 over pi. Sorry, just summation pi. Yeah, 1, right? Because the probability is sum to 1. So what we have shown is that for Shannon codes, the expected length is less than hx plus 1. And we already know for any prefix code, expected length cannot be more than 1, more than hx. So therefore, we have found codes which are in this very narrow window between hx and hx plus 1, right? So we have already gotten super close to the entropy. We are like 1 bit away from entropy. Is that okay? Okay. And there is something called a dyadic distribution where all the probabilities are powers of 2. We have been seeing some of those in our examples. So when you have things that are all powers of 2, then your logs become perfect integers. Your ceiling functions are equal to your x's. And for those very special cases, you have the expected length actually equal to the entropy. So you can like exactly achieve entropy for these dyadic distributions. And actually you can't achieve entropy exactly for any other distribution. So dyadic distributions are really the only distributions. So dyadic just means all probabilities are powers of 2, like 1 by 2, 1 by 4, that sort of thing. But you can get very, very close, as we'll see in the next or today later. Okay. So Shannon code is within 1 bit of entropy. That's what we showed. Now some of you who might have been like observing very closely might remember that I promised that we will get arbitrarily close to the entropy, right? This doesn't seem like that. We are like 1 bit away from entropy. If your entropy is like 0.00001, then I am like 1.00001. I am like thousands of times more than entropy. I'm very, very far away from entropy. So even though this looks like a very like powerful thing, it is not. There is still like a long way to go, right? So yeah, it is not quite arbitrarily close, right? This is just not true. Okay, so now I will ask you for help on an exercise. So you have a uniform distribution over 1, 2, 3. Just 3 things, uniform distribution. What is the entropy of this uniform distribution? Why is it log 3? Okay, because it's a uniform distribution, right? Yeah, we saw before that for a uniform distribution over k symbols, it's log k. So for 3 symbols, it's log 3. Can somebody compute log 3 for me? Log 3 base 2. Did you calculate or do you remember? Okay, nice. So I hear 1.58 bits, roughly. I think that's correct. Okay. Nice. For let's make a Shannon code. We have time. Let's make a small. So for Shannon code, like the symbols will have length this log 3 ceiling, so which is 2. So a Shannon code might look like this, where you have A, B, C. A is 0, 0, B is 0, 1, C is 1, 0. What is the expected code length of this Shannon code? So the expected length is 2 because all of the code words have length 2, right? Here the Shannon code is just the fixed length code we saw like a long time ago in the first lecture. Okay. So you already see this big overhead, right? 1.58, 2, and the bound is 2.58. It is like hx plus 1. So clearly the Shannon code is between entropy and entropy plus 1, but it's worse than entropy. It's like roughly 25% worse than entropy. There is a gap. There is a gap from entropy to Shannon codes. Do you think this code is optimal for this distribution? Let me make a new slide. Let me ask you. So yeah, let's do this properly so that we are on the same page. So we have this. So we have x, we have p of x, we have log 1 over p of x. So 2, 2, 2. And then we made this code word cx, which is like 0, 0, 0, 1, 1, 0. We can make a better code word, right? Better code. And I guess for the code word we saw, for this the expected code length was 2. Let's make a better code. So if we draw, let me just make it. So it's 0, 0, 0, 1. We don't need to have this 0 after 1. I can just make it a 1. This is still prefix free. And we computed entropy was 1.58 before. Okay. So what is the entropy? What is the expected code length of this guy? 0, 0, 0, 1, 1. Few people say 1.67. Let me just check. So it's 2 by 3 plus 2 by 3 plus 1 by 3. So it's 1.67. Nice. See, we got close. We got closer. Right? We were at 2 bits. Now we are at 1.67. So this code that you see on the far right, it's a Huffman code for this distribution. And that's our next lecture. It is the optimum code for this distribution. You cannot do better than this. But it's not still at entropy, you might observe, right? It's still 1.67 versus 1.58. There is a gap. Anybody has ideas how we can remove this gap?
Is it like for every epsilon that for like every degree of closeness, there exists a length of the alphabet? So you would have to have like a much longer alphabet.
But this is the alphabet you are given. How can you create a bigger alphabet starting from this? I see a few results. Yes. So both of you are on the right track, basically. Block coding, right? You need a bigger alphabet in this case, right? This alphabet, you can't do better, right? There is only so much like with one symbol you can do. But you saw in homework 1, if you remember, you had a uniform fixed length code over 9 symbols, and then you made it over 81 symbols, and you got better, and then you can keep increasing it. And the result will be something like that like for every epsilon, there exists a block size n such that you can get within epsilon gap of the entropy. So that's what we mean by arbitrarily close. Right. So clearly we are not at achievability. We are like not there. So this thing we will solve with Huffman code. We saw that Shannon codes are sometimes just bad, like they and you will see an example in the quiz today where they're like absurdly bad. So Huffman code is the solution here, and you will see that in the next lecture. Somebody says block codes, right? And block codes are good, right? So they can achieve entropy. You can show that they achieve entropy. We will probably do that early in the next lecture. But there are issues with block codes. It just gets exponential. Bigger and bigger blocks, you have to keep around these huge tables. It's exponential complexity. It's not great. So we will first look at block codes. Then we will look at something called arithmetic codes, which get the same result but much more efficiently. And then we will look at something called ANS, which again gets the same result but even more efficiently. So there is a sequence of codes, all of them used in a bunch of real life data compressors. They're themselves data compressors. Yeah, so this will be like sort of the plan for the next two weeks, basically, to look at all these different codes and understand there are various very cool ideas, like Huffman codes are based on trees, arithmetic codes are based on arithmetic, ANS codes are based on some number systems and so on. We have 4 minutes. Let me do something on block codes, unless we have questions. Okay. This will be very short and simple, and then we'll do some examples in the next lecture. This is just so that you go home satisfied that we have proved that you can achieve entropy. Okay. So if you code in blocks of n symbols, what will happen? So if you remember that the entropy of xn was, if you have like IID symbols, right, you have independent identically distributed symbols. So the entropy of xn was n times hx. I hope everybody remembers. Okay. Now, the Shannon code on n symbols will obviously be bigger than entropy. You cannot beat entropy. And it's less than the entropy hxn plus 1. Yep. Let me write down the this thing. I expanded the entropy term. Let me divide by n, right? Because what we care about is per symbol how much I'm paying, not per block. So per symbol is like divided by n because I have a block of n symbols. Done. That's it basically. Yeah. If you work in blocks of n, you can get within 1 by n of entropy. Yeah. Before we go, let's quickly look at this example. I think this might be interesting, right? Here we didn't do in blocks at all. Okay, so this is not a good. In the next lecture we'll do an example. But everybody able to follow this? So we basically code in blocks of n symbols. So what you do is you take n symbols, like you did in the first quiz, and you code over that joint alphabet, right? So if you had ABC before, now you have AA, AB, AC, ... right? You have 9 symbols. You make a Shannon code, you make a big tree with 9 symbols. Then you code those 2 at a time, sort of, right? 2 at a time. And Shannon code, the property holds for any distribution, right? It will hold for the joint distribution also. It will hold for the n tuple also. The same property, this property that we proved before, that you are between hx and hx plus 1. That holds for arbitrary things. And then you divide by n and you get basically this result that you can get within 1 by n of. So within 1 by n of entropy. So this is what we call like arbitrarily close, right? So this is the proof of the achievability part. Yep. Okay. Happy to answer any questions. It's my office hour, I believe, today.